Hello and welcome back to another very special episode of Statistical Awesome Ninja Moves with Dustin Allen Fife. Today we have a very special guest. Please, everybody, welcome Mr. Albus Dumbledore.
Thank you. Pleasure to be here.
You sound different.
Oh, must be the cold.
No, that ain't it. Oh, I know what it is. Aren't you like the first Dumbledore?
I'm the only Dumbledore.
Oh, no. Like movies 1 through 3 and then they replaced you with that other guy?
I don't know what you're talking about.
Yeah, I'm pretty sure you're dead. Like in real life and in the movie.
Resurrection Stone, my boy.
Ah, yes, of course. Nice hat.
Oh, you like it? It's my wizarding cap.
Make it.
Yes, with magic.
And a piece of paper. And tape. All right. Beautiful. So today we're going to be talking about visualization in regression. And with that, I'm going to introduce you to something called FLEXPLOT. So FLEXPLOT is short for flexible plotting. So it's a function that I created. It's within the Pfeiffer package currently. And the cool thing is, before we had to learn uni.plot, bivariate.plot, interaction.plot, and those sorts of things, and the visualize function. And I just decided to collapse those all into really just one plot. And so FLEXPLOT can do anything that the other plots can do. So now you only have to remember one function. So the formula of it, or the format of the function, is similar to how you'd write a linear model in R, something like that. So it's just FLEXPLOT y, whatever you want on your y-axis, tilde x, whatever you want on your x-axis, and data equals d. So I'm going to show you lots of examples. So for example, if you were to do a histogram or a bar chart, normally we'd use the uni.plot function, but now we're going to use FLEXPLOT. So we got FLEXPLOT, open parentheses, income tilde 1. And that's just R's notation for tilde 1 means just fit and intercept. And I kind of stole that notation just to say, hey, plot the histogram of income. And you see it on the top right there, and gender on the bottom right. So again, to do a univariate plot, it's just whatever variable tilde 1. And then, of course, comma, data equals d, or whatever your data set is called. And how about bivariate plots? Well, this would replace the bivariate.plot function. So you can do, for example, kind of a chi-square association type plot. And so you see that in the top right there. And so to get that, you would just use the exercise data set. And so therapy.type tilde gender, and it will just do an association plot there. If you want to do a scatter plot, which is the bottom left, that would be FLEXPLOT weight.change tilde motivation. And the function already knows how to do these things. And of course, my favorite way of plotting categorical variables, bottom right, is, again, exact same notation. Well, very similar to uni.plot, except you don't have to surround it in parentheses and that sort of thing. You just write it as a formula. So, wicked awesome. Am I right? Ah, that damn dog again! Always making noises! Give me a second here. And it seems the accent has changed. Give me a minute. Bother! Can't believe that dog. Oh, wait. Different character.
Oh dear, that was troubling indeed. Yes.
All right. So other plots that we can do. Actually, Dumbledore, you want to take this one?
Yes, I do say that FLEXPLOT is quite magical. So in the top right, we have weight change tilde therapy type plus gender. And so, oh, I'm sorry, that's the bottom plot. So that is an interaction plot, or one version of an interaction plot. And in the top right, we have weight change tilde motivation plus gender. So we can look at an interaction effect. Oh dear, I'm messing myself up here. You get, I'm going to turn it over to you because I cannot hold this accent and think at the same time.
All right, understandable. So I think Dumbledore, and Dumbledore just passed out. So Apparently, he's not going to be joining us today. You know, it's probably because he's died twice. Anyway, so yeah, top right, that's what you would typically see with a factorial ANOVA. Bottom right, that's what you would see for an ANCOVA or a visual representation of the ANCOVA. And let me just introduce you to some options. So, for example, the bottom plot shows some scatter plots, and what we could do is we could say SE equals false, which SE stands for standard error. And the bottom right plot does not have the standard errors, but the bottom left plot does. And then method equals LM, so it defaults to a lowest line, but you can instead ask for a linear model equation or just a regression equation, whatever you want to call it. And then you guys are familiar with that notation, the require cal plot, which allows you to plot in a grid, plot two side by side. So again, you can show confidence intervals, or you could modify the type of line that is being used. All right, you could also modify what sort of data is being displayed. So sometimes, occasionally, you know, I like to default to showing the raw data, but you can tell it not to show the raw data. So that's that command right there, raw.data equals F or false, if you want to spell it out. Or another alternative, so sometimes if you've got a massive data set, like if we're looking at the NSDUH data set, it's got tons and tons of data points and it just obscures things. What you can do is you can choose to sample it. And so you say sample equals and then however many data points you want to show. And so that's, so in the bottom left here, that shows the raw data without any of the options. This shows it without the raw data. Oh, did I? Anyway, whatever. And then the bottom right, or the right, because there's only one plot, shows sampling just 50 points. And of course, we could use calplot and show it in a grid. Woozah! All right, so practice. Now it's time for you to take out the exercise data set, and I want you to plot the following using FLEXPLOT. First is a mean plot of motivation and rewards, both with and without raw data. So make sure to do this in advance and come prepared, show me what you got, and also write down any errors that you get so I can either debug FLEXPLOT or debug you, dude. All right, then show a histogram of rewards, a scatter plot of income and weight change, both with a lowest line and a regression line. Bonus points in this assignment you're not getting credit for anyway, meaning nobody gets points, but good practice, yay. Put those in the same plot. Next, do an interaction plot between motivation, rewards, and therapy type, both with and without raw data, and an ANCOVA plot predicting weight loss from motivation and therapy type. Y'all got it? Practice, y'all. Go ahead, I'll wait. All right, hopefully that was awesome. Hopefully you didn't look ahead at the PowerPoint and realize I'm going to give you the answers. But in case you were interested, this is how you would do each of those. So yeah, enjoy, y'all. All right, so now that we have covered FLEXPLOT, let's go ahead and talk about graphics and multiple regression. Up until now, essentially, graphics have been pretty easy. You got a regression, you do a scatter plot. You got a t-test, you do a box plot or mean plots or something like that. But it gets a little more complicated in multiple regression. But FLEXPLOT makes it a whole lot easier. Oh, snizzap. All right, so in regression, like I said, how does one represent regression via a graphic? You use a scatter plot. So what are the advantages of a scatter plot? They are many. I thought it was going to show it right there. So advantages of a scatter plot, well, it shows all your raw data right there. So it's basically impossible to lie. It's intuitive to understand. It's awesome, and it'll bring peace, happiness, and joy for the rest of your life. Those are basically the advantages of scatter plot. Now, what about multiple regression? How do we visualize it? Well, I have seen 3 suggestions in the literature, and I'm adding a fourth, which is FLEXPLOTs, which is basically just coplots, but prettier and not as weird. And by the way, the plots that I'm going to show you, I didn't really invent them. per se. I see people doing similar things like this, but hopefully I will get credit and be famous and win a Nobel Prize for systematizing things. Okay? So if anybody is on the Nobel Prize committee, nominate me, y'all. All right, so what is a 3D plot? So basically what we do is we plot the first predictor on the x-axis, the second predictor on the z-axis. So z is the one that is coming from the screen out to stab you if you want to think in 3 dimensions. So the advantage of this is that all the data are there. There is no such thing as hiding bad data, unless you delete the outlier or something. But anyway, you get the idea. So disadvantages, it requires some rotation. So if you look at the plot at the right, it's really hard to tell which data points are coming toward you. I mean, it just looks like a simple scatter plot, but that can be masked by the 3D-ness of the data. And so in order to see really what's going on, you have to be able to rotate it. But even then, it's like brain bending and stuff. Like, it's really hard to figure out what's going on. You really have to twist your brain to think about it. And it requires some special software, or you could use R. R has probably 2 or 3 or 4 or 10 or 1,000 different packages that allow you to do 3D rotated plots and that sort of thing. And again, how do you interpret? Well, kind of hard. Kind of hard to conceptualize and that sort of thing. So for these reasons, I don't like doing 3D plots. But just for practice, in case you find them intuitive, in case you are the 1 in 10 billion that can think in 3 dimensionals and understand it as clearly as Visine in the eyes. Okay, that was a dumb metaphor. What? Visine in the eyes? Really, dude? Anyway, so what I want you to do is using the weight change data set to predict weight change based on health and motivation. And to see how you can do scatter plots, I think it's funny. I probably about once a year, I try to do 3-dimensional scatter plots. And that's probably been happening for the last 10 years. And I think every single time I look it up in the last 10 years, I go to that exact same website. So that website has sentimental value for me, and it sometimes makes me cry. Now go practice. All right. And in case you got stuck, hopefully you tried it first. Here's how you visualize multiple regression. So I'm going to read in the data set. Like I mentioned, I think it was last week, you actually don't have to read in data sets anymore. I don't remember the name of the data set, but I think it's, if you just type in data, open parentheses, exercise underscore data, close parentheses, it'll load the data set for you, and it'll be called exercise underscore data. Anyway, so in order to do, I think this is the way that I default to doing it, is through the RGL package. And what you do is you type plot 3D, open parentheses, and then whatever is, excuse me, on the y-axis goes first, and then I don't remember, I assume x comes next, and then z comes last, but play around with it, see what you get. All right, so that was the first way of visualizing multiple regression. The second way is called added variable plots. So this was actually the way that I was taught to visualize multiple regression as an undergrad when I was taking a intro to stats from the stats department at Brigham Young University. And they used the book Kuttner, Voxheimer, Niter, or something or other. Anyway, this is what they taught to visualize regression, and it's got a lot of advantages. So basically, it's a 2-step process to do an added variable plot. The first is that you residualize a regression model. So let's say you want to look at the relationship between weight change, motivation, and health. Well, one way you could do that is build a model with weight change and motivation. And then what you do is you can plot the residuals of that model against the new variable. So that's why they call it an added variable plot. You're adding a new variable to the model, and you want to visually see whether there's, or the strength of a relationship and that sort of thing. And so basically the advantage of this is that it, well, yeah, okay, skipping it, well, I wrote it twice. So advantage of this is it matches exactly what regression is doing in the background. So regression, remember how I said that it's like an angry parent who says, if y'all are going to fight about it, nobody gets the toy? Well, it's the same idea. If two variables are sharing information and equally able to, and that information predicts the y, then nobody gets credit. Instead, you get credit for your unique contribution. And so by residualizing the first independent variable or the first predictor variable, it shows the contribution of the next independent variable above and beyond what it had before, because again, that effect is subtracted out. Another advantage of it is it is very easy to interpret. You just look at it like you would a scatter plot. So in this situation, we have residualized motivation from weight change, and now we're looking at health. And it looks like there is a curvilinear relationship between the two, even after we have controlled for health, as they say. So the disadvantage, you can only visualize one variable at a time, which is unfortunate. Probably the bigger problem, I would say, is that you can't detect interactions. And also, it doesn't tell you whether, well, you can't detect nonlinearity. And let me qualify that. You can't detect nonlinearity in motivation. So if you just residualize without visualizing weight change on motivation, then you wouldn't know if there was a nonlinear polynomial term associated with it or something like that. And so basically, whatever you're residualizing on, it's going to assume that there are no other effects associated with that variable, which may not be the case. Does that make sense? If not, remember, write a question down and bring it to class, or,
as they say, if you have any questions, you can write them in the comments below, and otherwise we can talk about them in class.
All right, so disadvantages. Oh, we already talked about that. So how do you interpret? Well, you just interpret it just like a regular scatter plot. But remember, this shows the relationship after controlling for the main effect residualized variable, not nonlinearities and not interaction terms or anything like that. So that's an added variable plot. So for your practice, I want you to plot the exact same relationship you plotted before, which was, I don't remember. Okay, weight change, motivation, and health. But let's residualize health first and then do a second plot where, okay, so residualize health and then do an added variable plot with motivation and those residuals, and then do a second plot where you residualize motivation first and then look at the association between the residuals and health. Make sense? And by the way, that's good practice, especially if you're doing added variable plots, to look at it multiple different ways just to make sure you're getting the picture that you ought to be getting. All right, so to do it, pause! Don't look. Do it yourself. I'll wait. And then check your answers. All right. So the top plot, so I'm going to omit the data because in the exercise data set, there are some missing data. And we're in the next couple of weeks, we're going to get missing data and figure out ways you can do this. But anyway, just for now, we'll go ahead and omit the missing data. Again, we're going to run a linear model between weight change and health, and then save the residuals. So I'm creating a new object called $health.residuals, and then that is equal to the residuals of the model. And by the way, I omitted the data set, or I omitted missing values in the data set, because if you don't, here's what will happen. You will run a linear model between these two variables, and what R is going to do in the background, I think it's a terrible default, but that's what it does, is it just deletes any rows with missing data. And so the residuals, let's say there are 5 missing data points and there are 100 observations. And so this regression model will have 95 observations, and there will be 95 residuals associated with this. And the original data set has 100 because, again, the model deleted those 5 data points. And so when you try to add an object with 95 observations to an object with 100 observations, it's going to bark at you and say it can't do it. So that's why I omitted the data here. And then here's the FLEXPLOT command. Of course, you could do SE equals false or method equals LM to get a linear regression without a standard error. And then here's the opposite, where we residualize motivation instead of health. And let's see if we can pull anything out of here. So it looks like there may be some nonlinearity, but oftentimes I find that happens with Loess, as they are heavily influenced by the lower data points. If it weren't for these two, it wouldn't be. So I wouldn't interpret that too much, but it does seem to be that there is a slight positive relationship between motivation and the residuals after we've taken out health. And as far as health and motivation residualize, or I'm sorry, weight change residualized from motivation, there seems to be a negative effect, and that does look like a stronger polynomial term there. So if I were to run the entire model, so these results seem to indicate that the model should be weight dot change is equal to motivation plus health squared, because again, there seems to be a polynomial going on here. Cool? Y'all get that? Oh, look at that. I already interpreted in advance. Sweet. All right. Yeah, we already covered that. So now, like I said, added variable plots have the limitation that they don't tell you about interaction effects or anything like that. So now I'm going to get into FLEXPLOT and conditional plots. So FLEXPLOTs from the Pfeiffer package are really just coplots. They're just prettier and less confusing in my increasingly humble opinion. All right, so the style for and basically the notation is exactly the same. So if you're doing a Cleveland style conditional plot, by the way, Will Cleveland is the guy who invented conditional plots, or coplots for short. And the notation is y tilde, whatever your x-axis variable is, and then you've got that, which, which we call a vertical pipe. And you can interpret that as given. So this is saying y, or weight change tilde motivation given health. And what that will do is it will put health in, it will basically bin health. And so how you read a Cleveland coplot, let me make sure. Okay. So the bottom left shows you the lowest values of health. And you could look up at this right here, and it tells you that the lowest values range from less than 10, and then wherever that bar ends, so maybe, I don't know, 26, 27. So these are the scores of those who have, or this is the relationship between weight change and motivation for those whose health is below 27, basically. And then the next plot shows the health for those who are, I don't know, 21 or 22 up to 30. Okay, and so you'll notice there's some overlap here, and that's intentional in Cleveland's plot. Anyway, and then so as you go from bottom left to top right, it gets bigger. Does that make sense? And the rationale for that is when you read a plot on an x-axis, you always go from left to right, small on the left side to large on the right side. And on the y-axis, you go small at the bottom to large at the top. And so Cleveland is just following this convention, and now health gets bigger as you go from bottom right to top right. I didn't quite get that the first time I saw a coplot. It seemed kind of weird to go from bottom left to top right, but that's exactly why he does it. Make sense? So that is a Cleveland style coplot. Now a FLEXPLOT again is basically just a coplot, except I think it looks prettier. And so the notation is exactly the same. We're saying, all right, weight dot change tilde motivation given health. And so what it will do is it will look at the relationship between weight change and motivation by binning health. Now one difference between FLEXPLOTs and Cleveland style plots is he has overlap between his bins and I don't in mine. And that is strictly because I haven't figured out a good way of doing that. There's probably a way to do it, but I just haven't figured it out. I'm not sure that it actually makes a difference. I know there was a reason he did it. I can't remember off the top of my head why he did it. It may just be so there's more data points in each plot, but anyway. So that's Cleveland style conditional plots versus the FLEXPLOTs. So yeah, we already covered most of this. So the advantages of a coplot is all the data are there. Some of it is represented more than once because, again, you got this overlap, but all the data are there. It detects interactions natively, and how you can tell is if the slope of the line, oh, I forgot to mention. So right here, panel equals panel.smooth. Basically, that's telling R for every panel, which every one of these subplots within the plot, I want you to use the function panel.smooth. And so panel.smooth just happens to put a red lowest line. That's all that's saying. And so basically, you can detect interactions if the slope changes. And I'll show you some examples here in a minute. Another advantage is that you can visualize multiple variables simultaneously. So unlike an added variable plot where you could only really look at main effects one at a time, here you can look at interactions and you could do it simultaneously. Disadvantages is it requires some practice to interpret, and it's really tough to visualize more than 3 predictors. And basically, if you want a third predictor, you would just have another panel right here. I'm not going to show those to you because I'm going to show you those in FLEXPLOT because I think they're a little easier to interpret. But still, if you got 3 predictors and you're able to visualize them, you're doing pretty good. All right, so what do you look for? Like I said, interactions, if the lines are not parallel. If you're looking for main effects on the motivation variable in this case, which is the x-axis, you just interpret it like you would a standard regression. So it looks like across all these, there seems to be some sort of relationship. So at the bottom end, it's a positive, weak-ish relationship. And then at the top, some funky possible curvilinear things start happening. So this tells us that there may be an interaction effect because, again, the relationship changes for different levels of health. But at least at certain points, there's certainly a relationship between motivation and weight change. And so now if you wanted to look at main effects for the health variable, what you're looking for is if there tends to be an upward shift in the data. And I'll give you an example of that here in a minute. How about right now? So here's an example of an interaction. Oh, slope of the line change. Oh, okay, I see. So here's an example, this is just simulated data of an interaction effect. So if you look at the top right, which is the highest value of x2, there's a very strong slope, very steep line, whereas at the bottom left, there's almost no relationship. There's a very, very small relationship. And everything in between seems to be gradually getting bigger. So this is a interaction effect. So you could say that there's an interaction between x1 and x2, and as x2 increases, the strength of the relationship between x1 and y increases. Does that make sense? All right, and so here's an example of a main effect of x2 with no interaction effect. So basically, if you look at the y-axis here, notice that all the data points in the bottom left plot fall well below 1. Whereas in the top right, they fall primarily at about 1. And so there's this kind of upward shift. So this bottom right plot tells you there's a main effect of x, again, because there's a linear relationship between the two. And there's a main effect of x2 because the dots tend to get higher as you go up x2. Make sense? So let's go ahead and do some practice together. And I want you to ask yourself if there is an interaction here, if there seems to suggest that there's some interaction going on. And also ask yourself if both predictors have main effects. So what about this one? Okay, so there's clearly a main effect for pred1, whatever that is. And as far as the second one, it doesn't seem to indicate that the dots are shifting one direction or another as the plot changes. I mean, you see on the upper end of pred2, there's more data points at the upper end, but I don't know, it doesn't seem to be like much is going on there. Also, doesn't really seem to be much of an interaction effect going on. There's slight curvilinearity at the lower ends of pred2, and that kind of straightens out at the upper end, but that doesn't seem to be that big of an interaction effect. All right, so now let's look at another one. And so looking at it, it's clear that there's a relationship. There seems to be a strong linear relationship between x2 and y. And also there seems to be a main effect, because notice that the data points down here tend to be at the bottom of the graph, and the data points up here tend to be at the top of the graph. And by the way, if you see a lot of blank space in a plot anywhere, in a coplot anywhere, that probably means that there's going to be a main effect of the given variable going on, because this is going to default to showing the entire range of the data. And so you got white space here and white space here, which means there's a shift that has happened. As far as interaction effects, not terribly strong here. All right, so now we've got a relationship between pred2 and pred1. So there does seem to be a relationship, a strongish relationship here and there between pred2 and outcome. And there's clearly an interaction effect, because here we've got a positive slope, whereas here we've got a negative slope. And is there a main effect of pred1? Well, it really doesn't make sense to interpret main effects when there's an interaction effect, but we'll do it anyway just for the practice. But there does seem to be a shift. There's a lot of white space here and a lot of white space here, which seems to say that things are shifting as pred2 increases. All right, so with that, that's Cleveland plots. They're easy to use, but like I said, I think flex plots are more intuitive, and it's exactly the same way. You got weight change tilde motivation, so that says weight change is on the y-axis, motivation is on the x-axis, and then given income, and what it's going to do is it's going to bin income. And then data equals D, and you've already seen these commands. Method equals LM, SE equals F or false. And you also have the option to tell R exactly where the breaks are going to happen. And so you'll notice in the labels here, you got 95,000, 100,000, and 105,000. So there are 3 break points. And so what you can do is you can tell FLEXPLOT where the breakpoints are going to happen. And the number of breakpoints is going to be 1 less than the number of panels that you want. So if you wanted 6 panels, you're going to have to specify 5 breakpoints, if that makes sense. And then with the labels, it's kind of funky notation. This is just the way that R has to do it. Well, there's a reason for this, because I'm going to show you here in a minute that you can have both column panels like you have here, as well as row panels. And so you have to specify this as a list. If you have questions about this, we could talk more in class. But you have to specify it as a list, because you might want to name the row labels too. So you'll notice that I just say less than 95K, and that shows up here, less than 100K, etc., etc. So that's what the breaks are doing. So let's go ahead and interpret this. You interpret this exactly the same as a coplot, a Cleveland style coplot, except you don't have kind of how Cleveland has. You've got this wrapping, this snaking going on as you go from bottom left to top right. You don't have that anymore. So you just kind of interpret them in sequence. So in this situation, the lines are not parallel, so that indicates that there may be a possible interaction term. It's kind of a funky interaction term, because it seems to be stronger in the middle parts, but weaker on the ends. That actually may indicate that there is a nonlinear relationship there. White level may change a little bit. You know, you got empty space in the bottom 2, you got more empty space in the top 2, so maybe income has a main effect, indicating that people lower in income have less weight change or more weight gain or less weight loss, whereas those who are more wealthy, by the way, these people are making money! I want to hang out with them, huh? Get on their will. Anyway, so lines are generally positive, not flat, indicating a main effect for motivation. So the motivation, generally they're not flat. Okay? So, and we could go even further. Like I said, you can do it both in the columns and in the rows. And so here we have, looking at the relationship between weight change and motivation conditional on health in the columns and income in the rows. And so, like I said, this is why you do list open parentheses C, and then you specify under the first C how the columns are going to go, and under the second C you specify the breaks for the rows, and then the same thing goes for the labels, if that makes sense. So, oh, I'm sorry, I reversed that. So the first is the rows and then the columns. And you'll see that the labels correspond here to what they were here. Now, one thing to be careful about is obviously there's a whole lot of stuff to look at here. In fact, we've got 4 variables here. We've got motivation, rewards, income, and health. So we are visualizing not a bivariate relationship, not a trivariate relationship, not a quadvariate relationship, but a, what comes after quad? Well, there's like pentagon. So pentvariate relationship? I don't know. I might have just made up a word. But you're visualizing the relationship between 5 variables at a time. So that is a whole lot of cognitive load going on. But at the same time, this is the best way that I know of to include all that information in one. And so you might, for example, look at the difference between no rewards and rewards. It seems there's an interaction effect going on because they're not always parallel, especially when income is relatively high and health is really good. Okay? And interpreting these is going to take some practice and some theory to identify where you're going to look to figure out where the differences are, if that makes sense. Oh, look at that. It looks like I might actually show you how to interpret these plots. Oh, no, I'm not. Okay. Good luck. All right, so choosing which variable goes on the x-axis. So how do you choose which variable goes on the x-axis? Because, you know, in this plot we had 4 variables that could, well, yeah, I guess you could do 4 variables that could go on the x-axis. So which one do you choose first? Well, one thing that I've done is run a regression model first. And I'm totally violating my own 8 steps of data analysis by running the regression first. But there's a reason for this. What I'm not doing is I'm not looking at the p-values and I'm not looking at the effect sizes necessarily, but I kind of sort of am. Because what I want to do is I want to find which of those variables has the largest effect. And then that's what I'm going to put on the x-axis. Does that make sense? And also, it gives me a first cursory look. Now, at this point, you're probably more in EDA mode rather than CDA mode. So running the regression first doesn't really matter anyway because you're being honest about the fact that you're peaking in advance. But anyway, what this can help you do is it can help you decide whether certain variables have teeny tiny effects that you don't even care about. And it also tells you which variables are most important. And so what I choose to put on the x-axis is the variable with the largest effect size, if that makes sense. So if you were to run this code, I should have showed the output, which I guess I didn't. Did I show it? Okay. So you can run this code and see for yourself. I'm not going to do it here, but if you run the estimates, it's going to show that motivation has the largest effect, followed by rewards, and then income. At least that's the way that I tend to do it, is you put the first variable here, then the second. Actually, no, that has a different reason. I put rewards here because it's categorical. And by the way, anything to the left of the pipe is either going to go on the x-axis or it's going to be put into categories like this as separate lines / separate symbols. So hopefully that makes sense about which one goes on the x-axis. So let me interpret this. So the lines are fairly parallel, meaning there's no real interaction. Scatter across the y-axis doesn't change much. You got a little bit of empty space here and a little bit here, but it's not that big. So it tells you that income probably isn't making that big of a difference. And rewards are consistently higher than the no rewards. So we've got the dashed lines conditions are always higher than the no rewards conditions. And so this plot seems to suggest that there's a strong relationship between motivation and weight change. There's a little bit of something going on possibly in income, and there's something going on with rewards. Okay? And one thing I would do, by the way, on this slide, I showed you which variable goes on the x-axis. What I want you to do is totally do that and then ignore what I said and then switch things around. because sometimes you gain greater insights, because obviously it's easy for us to see the relationship between this variable and this variable because we have a lot of practice in it, and it's just you got more gradation there, if that makes gradation, whatever it's called. But I would still swap those axes just to confirm what you seem to be seeing is that there doesn't seem to be a strong relationship with income. Make sense? All right. Oh, look at that. I just flipped it. All right. Man, I'm getting ahead of myself. So that will give you a different perspective. Like I said, here we said, well, it doesn't seem like the y-axis is shifting much across the different panels. And sure enough, there's not that strong of a relationship. But on the other hand, well, and that's the problem with putting something in the given axis, is it makes it look weaker than it really is. So we got some empty space up at the top here and empty space at the bottom here, which seems to say that they're shifting. But you would look at I guess more holistically, you can see that the dots are gradually shifting up, but it looks like it might be weak. But if we look at this plot, whoa, that's a strong relationship. So that's why it's important to kind of switch things out. And here's the R code that does it. I created an object that stores the FLEXPLOT, and then it must have been that the income was kind of messing things up, or the axis, the tick marks or the numbers were kind of bleeding into each other. And so that's probably what that does, is it's basically saying, all right, here's what I want to do with my x-axis or my x scale, is I want to break it into 3 categories, but it's like what we did with the labels, where we say give it 2 breakpoints, which is going to put 3 numbers here, and then pretty basically is a generic term for, I think in this case it means don't use scientific notation. I don't know. I forget. Look it up if you want to. All right, so what are we looking for? So top left, here's an example of a very, very, very strong main effect of x1, no interaction, and no main effect of x2. Here is a example of x2 and x1 having strong main effects. Again, the dots are going up as you go from left to right. Here is a main effect of x1, x2, and a, which is your categorical variable. Again, that's indicated by the difference in intercepts, basically, between the 2 lines. And then here we've got a main effect of x1. Again, there's a vertical linear relationship. x2, the data points tend to go up. And x3, where is no x3? What was that about? Anyway, forget x3. And an interaction between x1 and a. Because again, the lines are kind of deviating slightly more. It's not the strongest interaction effect, but these tend to be getting a little bit closer here and a little further apart here-ish. Okay, so hopefully that helps. So now it's time for some practice. Determine how health, motivation, and therapy type are related to satisfaction. And go. I'll wait. Or really, you should pause your video because I got to get going. Oh, and that's it. Okay. So that is how you visualize regression. Hopefully I've given you some excellent, awesome tools. And let's have a moment of silence for Professor Dumbledore. That was touching, thank you. And peace out.